today I will talk about the importance, or let's say relevance, of topography-driven groundwater flow in the Alpine regions with a case study from the Julian Alps. So this was also a part of my PhD research and was prepared with the help of my colleagues from Geological Survey, as well as in cooperation with Judith. Okay, so the water cycle. We all know that the water cycle illustrates the fundamental physical processes on Earth, but it would be very interesting to ask ourselves what is the role of the regional groundwater flow within this cycle. I would say this is quite a complex question because changes in precipitation don't affect all parts of the cycle equally. So the regional groundwater system, especially in mountains, for example, responds differently and more slowly than the shallow flows. So understanding these systems is crucial for managing water resources, especially today as the climate change brings much more variability. I believe that topography in this case is a key factor because it shapes hydraulic gradients, flow depth, and of course, consequently also the chemistry and the age of groundwater. As you all probably know, the regional groundwater flow refers to deep, large-scale circulation system, which is controlled primarily by topography and based in geometry. So if we put that in the context of the Alpine regions, we can say that the regional groundwater flow in the Alpine basins is fundamentally gravity-driven. And this variable topography and permeability promote the deep circulation and thermal convection under normal heat flow. So we could say that topography imposes strong hydraulic gradients and long flow paths, resulting in the advective heat transport. There are, I think, three principal hydrogeological features of the Alpine aquifers, and these are heterogeneous and complex lithological conditions, high hydraulic head differences, and high groundwater recharge. But if we really want to deal with Alpine aquifers properly, we need to address both the near surface zone as well as the deeper regions, because the shallow groundwater discharge in the Alpine headwaters provides base flow in rivers that originates in mountains, which is critically important for aquatic habitats as well as for the water supply downstream. And on the other hand, the deeply infiltrated meteoric water can increase its temperature and creating geothermal systems that can be utilized for heat and in some rare cases also for power production. On this picture or this figure, you can see the generally accepted conceptual model for geothermal systems in the Alps. And this conceptual model is based on 5 factors. These are precipitation and recharge at the highest points. Then we have infiltration and the vertical flow, percolation of infiltrated water into a deep system, heating and rapid discharge to the surface due to the forced convection flow. And what is very unique or specific for the Alpine regions is that because valleys are usually filled with the quaternary sediments, we have a formation of thermal plume. So for this mechanism to work, I think 3 conditions must be met. These are an extensive recharge area with infiltration into deep layers, a relative large difference between the recharge area and the thermal water outflow. And what we also need is a distinct hydraulic boundary, either in the shape of fault or any other lithological or stratigraphical boundary. So as already mentioned, the mountainous or alpine regions create unique thermal and hydraulic conditions that strongly influence the groundwater flow. So as you can see from this figure, in the recharge areas where cold meteoric water infiltrates quickly, the temperature profile is almost isothermal. I'll just show you. So this is the isothermal. This means that even at the greater depths, the temperature remains relatively low because the water is practically constantly moving downward and cooling the surrounding rock. Well, deeper in the system, we also encounter the low temperature horizontal flow, where water has not yet reached the full thermal equilibrium with the surrounding environment. So as water continues to move through the massive, the temperature profile slowly transits to linear geothermal gradient, which is reflecting in conductive heat transfer. So finally, near the discharge zones, especially where warm water rises rapidly, we can observe elevated near-surface geothermal gradients. We all know that the carbonate systems are very heterogeneous. So, for example, the effective hydraulic conductivity in karstic and karstic fissured aquifers is controlled by a dual porosity system. So on one hand, we have high conductivity conduits and low conductivity matrix, along with the exchange processes and geometric factors such as fracture density, conduit size, and connectivity. So the challenge here is how to really represent and apply these heterogeneities in the conceptual and numerical models. So the answer is hydraulic continuity, which is probably the most important argument behind the applicability of the regional groundwater flow for a carbonate system. So if we consider that, then the groundwater movement in the thick carbonate regions on a regional scale should be conceptualized and modeled as a cross-formational gravity-driven groundwater flow. Okay, so before we dive into the details of our Blade case study, or Julian Alps case study, I would like to show you just a little bigger geological picture. So on this map, we can see the basic geolithological map of the European Alps. And as you can see here, the Julian Alps are positioned in the southeastern part, mostly within Slovenia, but also extending slightly to Italy. So geologically, the Julian Alps are part of the southern limestone Alps, which are dominated by thick carbonate formation that extend practically from Switzerland all the way across the Austria and to Slovenia. Although we can see from this map that overall Alpine chain is highly diverse based on the geolithological settings, the southern belt is characterized by extensive limestone and dolomite units that form some of most prominent carbonate massif in Europe. Okay, so let's go to the thermal water and Julian Alps. So maybe just for beginning, I would just like to tell you that thermal water in Slovenia is a groundwater with a temperature of at least 20 degrees Celsius. 70 degrees at the point of discharge to the surface. This is according to Slovenian water law. We only have low temperature geothermal systems with highest temperature up to 200 degrees in the northeast part of the country in well-known Pannonian Basin, while in the western Slovenia, the earth heat flow is lower and also the expected temperature are below average. This is due to the greater thickness of the Earth's crust beneath these Alpine regions. And there's also another very important contributing factor. This is the thick sequence of carbonate rocks, which are mostly well fractured and karstified, and therefore allow deep circulation of cold meteoric water. For that reason, in the northwest part, so you can see in this figure, on northwest part of Slovenia, we don't have many thermal springs. Actually, 4 are known. These are spring Toplice in Bled, which have an average temperature at its outflow of 21.5 degrees. Then we have spring Zatulmin, it's located here, with the same average annual temperature. Then we have spring in Besnica, Zgornja Besnica, with the average temperature 20.5 degrees, and spring Straža and Spodnje Pirniče with the same average annual temperature. If we go to the Blade case study, so in my opinion, Blade case study offers practically a perfect pilot area for studying the dynamics of regional groundwater flow in so-called thick carbonate strata. So this study area is located in the northwestern part of Slovenia, as I already told you, and includes the eastern part of the Julian Alps. including the high karst plateaus of Pokluka here, Mežakla here, and Jelovica. This is just to have a basic idea on the regional topography in this area, which is, I think, quite important regarding the conceptualization of the groundwater patterns. And between Jelovica and Pokluka massifs, we have Bohin Valley stretching towards the Blade Lake here. And between the Pokluka and Mežakla massifs, we have Radona Valley also stretching towards the Blade Lake. This whole area is characterized by significant variability in the spatial distribution of precipitation, and due to the large altitude effects, also by substational temperature variations. So you can see from this figure here, that's at some part in the Julian Alps, we can get more than 3,000 millimeter of precipitation during the year. The average temperature, for example, at Bled is 9.5 degrees approximately, and we have a temperature gradient of approximately 5 degrees, which means that at the altitudes of approximately 2,500 meters above sea level, the average annual temperature is below zero. So the use of thermal water in Bled actually has a quite long tradition, especially for tourism and health resort. But the thermal water at Bled discharges from fractures in the primary geothermal aquifer, which is located within the carbonate rocks of Triassic age. The temperature is between 19 and 23 degrees, and it is utilized from thermal spring to Plice, shallow well VB2, and deeper well T9. So when it's discharging to the surface, most of the water infiltrates into the intergranular aquifer of Quaternary age, where we can observe a thermal plume, which develops due to the temperature difference between the thermal water outflow and cold groundwater in this shallow aquifer. This is a situation which I already mentioned when I was telling about the specifics of the Alpine case studies. So there's another important feature which needs to be addressed when dealing with alpine environments, especially the carbonate alpine environments, because in the carbonate massive, direct measurements of hydraulic head variations or fluctuations are extremely scarce. So the reason is actually quite simple. The drilling to greater depths in these areas is technically very demanding. And what is also important, it is very expensive. So we have little or practically no continuous data from the massive itself. And this is where the deeper cave system play a very important role. And Julian Alps are, I can say, famous for deep cave systems. You can see the table here. We have at least 9 cave systems which are deeper than 1 kilometer in Julian Alps. And on the bottom figure here, you can also see the example of Migovec cave system shown in geological cross-section. And I can say that such cave systems provides the most practical evidence for understanding how groundwater moves through thick carbonate massive. And they help us to somehow constrain our regional flow models. And what is the most important, to help us to set up proper boundary conditions. Okay, so I already said a few things about the geology, but nevertheless, so the Julian Alps consist of sequence of Triassic and lower Jurassic shallow water carbonate rocks with rare patches of deeper water, middle to upper Cretaceous carbonate clastic rocks. In this study area, these rocks are often overlain by oligocyanate sediments here, and of course also the quaternary sediments also in the valley bottoms as well as on the massifs itself. We also have volcanic rocks in this area which were formed as a result of tectonic movement and the rifting of an extensive carbonate platform during Middle Triassic, which was also accompanied by intense volcanism. And on the bottom figure, you can see a regional geological cross-section, which was actually prepared just for the purpose of this study. I have to mention also the Quaternary period because the extensive glaciations in Quaternary had a particularly strong impact on shaping the landscape. So the various interpretation has shown us that 3 major glaciers were active here. If you remember from one of the previous slides when I show you these 3 masses. So we also have the glacier named by them. So we have we had Bohin Glacier, Raduna Glacier, and Dolina Glacier. So at their maximum extent, the glaciers also cover parts of the Pokljuka and deposit large amounts of glacial fluvial sediments in some areas. And what is very interesting that also glaciers and post-glacier activity separate what was once a single massif of Pokljuka, Lovica, and Mežakla. Okay, so the majority of the area consists of large system of interconnected karstic fissured aquifers, where we can say that the surface runoff is minimal and most of the effective precipitation infiltrates towards the base level of the groundwater. We also have intergranular aquifer, as I already mentioned, represented by glaciofluvial, alluvial, and slope sediments. And the thickness of these sediments is in the valleys up to approximately 100 meters. Now I'll just briefly present the methods we used in our research. So we used a range of field measurements and laboratory analyses. So we had continuous measurements of groundwater level and temperature. We had discharge measurements, pumping tests, and chemical and isotope analysis. So all this help us to understand where the water really comes from, its source, how long does it travel, so the residence time, and all other geochemical properties which needs to be addressed when dealing with such case studies. We also applied groundwater flow and heat transport modeling. So for the regional scale simulation, we used feed flow and take into account both advective and conductive heat transfer. In order to build the regional model, we first took the geological cross-section that I showed you already at the beginning and grouped these geological units within similar hydrogeological properties into hydrostratigraphic units. So for the purpose of numerical modeling, these hydrostratigraphic units were then assigned representative parameter values. So below this hydrostratigraphical cross-section, you can see also the model domain together with the boundary condition that we used in our simulations. And for the purpose of the detailed analysis of thermal outflow and the evaluation of thermal plume, we also distinguish this local part from the regional model. So we use simple analytical model, and for validation of this analytical model, we also simulate local heat transfer problem with a numerical model. And if I just briefly present you the results of hydrogeochemical properties, so based on our literature data and new measurements, 37 water samples in the wider area were collected and analyzed using hierarchic clustering. So the sampling location, including standardized variables of major ions, were grouped into 4 clusters. So these 4 clusters show systematic differences in most of the analyzed parameters, and those reflects different components within the natural groundwater flux. I won't go into details. I just want to say that all samples, all water samples, were determined as a calcium bicarbonate or calcium magnesium bicarbonate types, which is typical, of course, for limestone and dolomite systems, which means that the chemistry shows us at the first step that the dissolution of carbonates is the main process which controls the water composition in this area. We also applied the isotopic composition of oxygen and deuterium, which suggests that the thermal water in Bled area, of course, is of meteoric origin. But what is very important that it recharging from the altitudes up to 1,500 meters above sea level. Just for comparison, the thermal outflow near the Lake Bled is on the altitude of approximately 480 meters above sea level. So what was also interesting was relatively high values of tritium, which means that the thermal water refers to possible mixing processes between the deep thermal component and the fresh shallow groundwater. This is in this quaternary sediments. That was also confirmed by some other chemical elements such as strontium, barium, and etc. Yes, so one of the important activities which we did was to determine the groundwater level as a boundary condition in the model domain. So we determined this groundwater distribution of the in three segments separately for the karstic fissured system, for the Oligocene layers, and for the quaternary sediments. In the karstic fissured aquifer, we use the elevations of the main springs and the data from the cave system from Euclidova Piščal. And the results on regional scale modeling show us that the regional groundwater flow show the large topographic differences in Alpine terrain really control the groundwater table. And what is important, they strongly influence the natural heat distribution and travel times. We simulated three scenarios, with one with homogeneous conditions, then with heterogeneous and isotropic condition, and heterogeneous and anisotropic condition. And what is really interesting is that already in case of homogeneous model, the high hydraulic gradients drive forced convection, leading to warmer discharge areas. And we can say also that the combination of topography and geological heterogeneity of this system creates a multi-scale groundwater flow system, which is ranging from very shallow up to, let's say, few 10 meters deep, to deeper hill slope flows up to few 100 meters, and finally deep regional flow paths more than 2,000 meter deep, which can also bypass surface hydrologic boundaries. The thermal water discharge in blade therefore arises from these complex flow patterns driven by substantial elevation contrast between the recharge and discharge zones and controlled by heterogeneous and anisotropic geological formations. Also, the simulations of Peclet numbers show us that the key role in the forced convection flow is played by a cross-formational package of these Triassic carbonate rocks that have a sufficiently favorable properties for advective heat transport. And the simulated ages of local groundwater flow in these unconfined carbonate regions are of the order of approximately 10 years, at most a few tens of years, while in the case of the thermal water, we can expect residence times up to 200 years, probably not older than 500 years. So we check that this result are also consistent with literature values for these similar alpine environments, where the groundwater transit time, especially on the hydrothermal circulations, is usually in the range of 10 to up to 1,000 years. But for example, in the low permeable Oligocene cover, the residence times, of course, are much higher. And then the local model of thermal outflow, we find out that the main recharge area is at the contact between the fractured dolomite and the intergranular quaternary aquifer. Models suggest us that the thermal water outflow rate in the main zone is in the range of approximately between 60 and 90 liters per second, which means that the total outflow of only 30 to 40% of the total outflow is captured today, while the rest remains hidden as a natural discharge in the glacial-fluvial sediments. Yes, and this is what I have prepared. Also for the end, there's a very interesting photo of the Zatolmin thermal spring, which is now our case study which we are dealing with. And you can see also the photo taken with the thermal camera. Okay, so thank you.